we are discussing some basic concepts from the theory of probability. And in this part, we'll be getting some idea about probability distributions. And it is a very important concept which will come again and again in many part of our modeling activities. In probability theory, we talk about random variable, and one example that we have been discussing so far is tossing a fair coin. And if you want to actually store the value in variable x, we have to choose this x properly. There are many popular distributions that we will need to learn, and I'm sure that you guys also have some idea about these distributions. One is uniform distribution. Then we have binomial distribution, multinomial distribution, and normal or Gaussian distribution. There are other examples of mathematical probability distributions, but we have just shown you few examples, and some of them are actually variable type dependent. For example, uniform distribution can work both for discrete and continuous variables. This binomial distribution works for binary and discrete variables. Then multinomial distribution is quite general for discrete variables, and this normal distribution only works for continuous variables. So let's get some idea. We have been talking about this throwing a fair coin, and we know that the coin has two sides, so head and tail. So head and tail both has 1/2 probabilities as their values. So we can generalize this for like any number of variables. For example, for n, it will be 1/n, and the function would look like this. Okay, so if n is 2, then we can connect back to our throwing a coin example. But if you put n equal to 6, then it is a throwing a dice example. When your variable is discrete, we call it as a probability mass function. Okay, so this is the probability mass function definition for uniform distribution. As I said, that this function also applies to a continuous variable, but the definition will change. Okay, so if you recall, for discrete is 1/n, and for continuous it's 1 divided by b minus a. A and b are actually their ranges, so we are only talking about this pink area. One example in the two-dimensional domain is throwing a dart, but you can think it as you want to sample any point in between a and b, and the probability will be 1 divided by b minus a. Actually, this is not the probability is what we call a function value. This function, we call it as probability density function, but if you want to estimate the probability, then you have to multiply this function 1 divided by b minus a with a delta, because the number of points are actually infinite between a to b. Okay, because we are talking about a continuous range. But again, nothing very complex. So the same distribution for discrete is 1 divided by n, and for continuous uniform distribution, the density function value is 1 divided by b minus a when x is within the range a and b, and 0 otherwise. Okay, and finally we'll be talking about a very popular distribution from the continuous variable case, which is a normal or Gaussian distribution. So 18th century mathematician Friedrich Gauss is the inventor of this distribution, and there are a lot of natural data phenomena that follows this distribution. For example, our height or weight. If you are developing a machine learning model, then you want to use certain distribution for their errors or measurements. So this is the distribution of choice for many practitioners. So imagine that we are talking about our height, and if you plot their values, it will form this kind of bell-shaped curve. Okay, the maximum number of data points that will fall around its average or mean, which is one of the parameters of this distribution. And the other parameter is sigma, which is the standard deviation, and the mass function definition is here. Okay, 1 divided by sigma, then root over 2 pi e to the power x minus mu squared negative divided by 2 times sigma square. Okay, these e and pi's, these are actually constant scalar. So there are some natural features of this distribution. Okay, so 68% of your data will fall within the 2 standard deviation from the right and left side of the mean. Okay, so these are proven facts. If you go to 2 standard deviation, then you will cover 95%. Okay, so that's why this distribution is used in many hypothesis tests and proofs. Okay, then there is a natural form of this distribution. Okay, the same distribution, but we actually center the mean at 0 and then make the standard deviation 1. Okay, so how can you do that? Using this formula. Okay, so you have a random variable x. If that x follows a Gaussian distribution, and if you subtract its mean and divide by the standard deviation, then we are transforming our normal distribution to another distribution which we call standard normal or Z distribution. Okay, the properties are your mean of your transform data will move to 0, and then the standard deviation of the distribution will be 1. Okay, so this we call standard normal or Z distribution. Okay, so that was the overall content for the probability basics. If you have any questions, feel free to reach out to me and I will try to answer.